students, welcome to a new session for the chapter Solutions. In the previous session, we have seen about the solubility of solid in liquid. Okay, in that we have seen various factors affecting the solubility of solid in liquid. Okay, we have also seen how does the temperature and pressure affect. In that we have understood how to apply Le Chatelier's principle for the effect of temperature. Okay, so now moving forward, today we will be doing about the solubility of gas in liquid. Okay, about the solubility of gas in liquid. If you have understood solubility of solid in liquid very well, now the understanding regarding the effects of various factors here will become very easy. Now, when we try to understand solubility of gas in liquid, I'll give you a very simple example before taking you into the concept so that your understanding is very clear. Or else, see, solid in liquid is something which you observe in your daily life because you keep on adding various things in your water. You add glucose powder in your water, you add sugar in water, you add salt in water. So, solid in liquid is something which is a very general observation. So when I'm trying to make you understand solid in liquid, I don't think I need to put more effort because those are the observations generally you do in your daily life. But when we come to the solubility of gas in liquid, I need to give you an example that way, a very very important example and a very easily understandable one. Now you people like cool drinks, okay, though it is junk food, you should not drink it much. Occasionally you people drink cool drink. Now when you take a new cool drink bottle and try to open the cap of the new cool drink bottle, what do you observe? You observe you observe some some sound coming, right? You observe some fizzy sound coming. Now, why does this sound come? Okay, why does this sound come? Okay, I think most of you people know. This sound comes because some gas is coming out of the cool drink bottle or any soda bottle. When you open the when you open the cap of a new cool drink bottle, you get a particular kind of fizzy sound, and that sound is due to the gas coming out of the cool drink bottle. Now, if you are thinking, okay, why does the gas come out? Actually, where is the gas existing? Okay, and when I open the bottle, why is it coming out? If I think you would have always thought about this thing, no? Why is this sound coming? And many of you people know that cool drink is a carbonated drink. Okay, most of us know that cool drink is what? It is a carbonated. Okay, cool drink is a carbonated drink. Okay, carbonated drink. When I say carbonated drink, what does it mean? What does it mean? You have water, okay, along with carbon dioxide. Okay, you have water along with carbon dioxide. Now, if you go to the chemistry part of this, it is not exactly as carbon dioxide. You have carbonic acid, and that carbonic acid will break down into CO2 and H2O. Okay, I'm not going into that part, but if you see here, okay, carbonated drinks are those drinks like your cool drinks and soda drinks. They are carbonated drinks. Means you have your water. In water, you have your carbon dioxide gas, and sugar is so obviously there. Now, it is not easy for me, it is not easy for me, like I mix sugar in water. I can't just take carbon dioxide and mix in water and tell that it is done. This is not that easy process because we are talking about a gas, and gas has the property of diffusion. It keeps diffusion process. Now, to keep what is carbon dioxide stay in water is a very difficult process for us. Okay, we have our water, in that sugar is obviously mixed because we are talking about a cool drink or soda drink. In that, now our job is to dissolve carbon dioxide in that. Now I can't just take carbon dioxide and add it in that. For that, what should I do? For this process to happen, what should I do? I need to apply some pressure. Okay, I need to apply some pressure. Okay, when I was discussing solubility of solids and liquids, I told pressure will not have any effect. I clearly told pressure will not have any effect in the solubility of solids and liquids. But when we come to the solubility of gas in liquid, it is not like that. Pressure will have a very major role in the solubility process. Now, when you apply pressure, when you apply lot of pressure, this carbon dioxide mixes with the water, and that becomes your carbonated drink. So, for carbon dioxide to be soluble in water, it is not easy. We need to apply lot of pressure so that the carbon dioxide gas gets soluble in water and we get our carbonated drink. Clear? Now, okay, we have mixed carbon dioxide in water and that had made our cool drink. Okay, and there is lot of pressure. With lot of pressure, carbon dioxide has been dissolved into your cool drink, and they close the cap. Okay, and they close the cap. Now, what happens? Now, when you close the cap, the pressure is fixed inside the bottle. Okay, the pressure is fixed inside the bottle. Under that fixed pressure, your carbon dioxide gas is dissolved in water. Now, when you open the cap, what will happen? When you open the cap, the gas will slowly, the gas which is there on the top. See, the cool drink is not completely filled up to the cap, right? You have some space. You have some space. Here you have your cool drink and here it is your cap. Now, when you open the cap, the gas which is there on the top part will come outside, and that will give you that, okay, fizzy sound. Okay, now what did you do? You got the sound, you opened the cool drink bottle and you poured the cool drink into a glass to drink. You're talking with your friends. Okay, so what happened is, initially when you took the first sip, it was very tasty. The cooling was very tasty because it had that carbon dioxide in it. It had more dissolved carbon dioxide in it. Okay, it had dissolved carbon dioxide in it. So when you are drinking the cool drink initially, it was very fizzy. It was giving you that feeling of the fizzy feeling. So you were feeling very satisfied drinking the cool drink. Now you are talking with your friends slowly. Your pace of drinking cool drink has been reduced. Now after 15 minutes or half an hour, okay, if you are only half done. If you keep drinking the cool drink after you poured in the glass. After half an hour, if you start drinking it, you will not get that fizzy feeling. You will feel as if you are drinking some sugar water. You feel as if you are drinking some sugar water. Why? Because when you have put it in your normal glass, okay, you are exposing it to the outside atmosphere. So you are ready. Okay, now what will happen? Previously, it was there under certain pressure, so there was lot of dissolved carbon dioxide. Now, when you have put it in the glass, the pressure got reduced and the carbon dioxide. Okay, the carbon dioxide will no longer be in the water, it will go into the atmosphere. So you will no longer get the fizzy feeling. So for the carbon dioxide to be dissolved in the water and for you to get that fizzy feeling, what is the most important factor here? It is our pressure. Okay, so pressure plays a very major role in in the solubility of gases in liquids. Now there was a scientist called Henry. Okay, there was a scientist called Henry who worked a lot to understand the concept of effect of pressure on the solubility of gas in liquid. So what does Henry's law? Okay, and in that process he has given a law. What is that law? And that story we'll definitely see. But before that, what does Henry's law tell us about? Henry's law, okay, explains quantitatively. Henry's law explains quantitatively the relation between the effect of pressure and solubility of gas in liquid. Okay, so what does Henry's law explain? Henry's law explains quantitatively the relation between the effect of pressure and solubility of gas in liquid. So how does the effect of, what is the relationship between the effect of pressure and solubility of gas in liquid? Henry tried to quantitatively explain the relation between the effect of pressure and the solubility of gas in liquid. Now I told you how, with taking a simple example, how does pressure affect the solubility of gas in liquid. Now to understand it in better way, let us take a small activity here and try to understand what Henry is trying to tell us exactly quantitatively, and that will lead to our Henry's law. Now if you see here, I have taken two beakers here. In two beakers I have certain amount of liquid. Okay, in two beakers I have certain amount of liquid. Now what did I do is, I started passing gas onto the liquid. Okay, I started passing gas into the liquid. After some time, I have closed it using a piston. Okay, I have closed it using a piston. Means what? I have liquid. On the liquid I have gas which I have passed, and on top of gas I have a piston so that no more gas enters. Now on the piston I have put a certain weight. Now when I have put a certain weight, this weight will exert pressure. Okay, this weight will exert pressure. Now I have put a weight, and this weight will exert pressure on the gas. Okay, this weight will exert pressure on the gas. Now when the weight is exerting pressure on the gas molecules will go into the liquid. Okay, the gas molecules will go into the liquid. Just like that, if I put the gas on the liquid molecules will not go into the gas. We need to apply some pressure. Now, when I apply that pressure, the gas molecules will start going into the liquid. Clear? The gas molecules will start going into the liquid. Okay, so from here, few gas molecules have entered into the liquid and they got solid. Now come to the second beaker. Okay, the same setup and everything is same, but here I have applied more pressure because I have put more weights on the piston. Okay, here I have put more weights on the piston. Now, as in that way, now I am applying more pressure here. Clear? I am applying more pressure here. Now, when I apply more pressure here, more gas molecules will go into the liquid. Okay, here less gas molecules will go into the liquid. Here more gas molecules will go into the liquid. Am I right? Here more gas molecules will go into the liquid. So from this, what can I conclude? What can I conclude? Okay, now here try to understand one thing. When I applied more pressure, more gas molecules went into the liquid. Now when I say more gas molecules went into the liquid number of moles of the gaseous component are increasing. Yes, here I applied less pressure, the number of moles of gas present in the liquid are less. Here when I applied more pressure, the number of moles of gas going into the liquid will be more. So can I say, in this case, the mole fraction of gas in this solution is less. In this case, as more gas molecules got dissolved in the liquid, the mole fraction of gas in this solution will be more. So can I say, pressure of the gas, okay, pressure of the gas, the more the pressure you create for the gas here, the more the gaseous pressure you create here, more will be the mole fraction of gas. Am I right? Am I right? The more the pressure of the gas above the liquid, okay, more the pressure of the gas, more pressure you apply on the gas, more gaseous molecules will go into the liquid. So the mole fraction of gaseous molecules is more in the solution. Here, as you apply more pressure, more number of liquid molecules will go into the solution. So the mole fraction of gas is more here. So from this, I can say that, okay, the more pressure you apply on the gas, the more will be the mole fraction of the gas. Clear? Now, here, okay, we can also call this pressure as partial pressure of the gas. Okay, because gas is exerting pressure, we can also call it as partial pressure exerted by the gas. So what is P here? P will be partial pressure of gas. P will be partial pressure of gas, and X is mole fraction of gas. X is mole fraction of gas in the solution. What kind of solution it is? It is gaseous solution, but it is solution only. Partial pressure of gas and mole fraction of gas in the solution. Now, okay, what did Henry tell is the mole fraction of gas in the solution is nothing but the solubility of the gas. Okay, the mole fraction of gas is nothing but the solubility of gas, because more the number of moles go into the liquid, more the number of moles of gas go into the liquid, the solubility of gas is more. So if I am saying mole fraction of gas is more, obviously the solubility of gas is more. So what does the mole fraction of gas indicate here? It indicates the solubility of the gas. So according to Henry's law, the partial pressure of gas is directly proportional to mole fraction of gas. Now what did he do is, he removed the proportionality symbol and he has put a proportionality constant. Now this proportionality constant, okay, because Henry was giving this law, he will be a little selfish, so he named it as Henry's constant. So what is KH here? Okay, now KH is your Henry's constant. KH is your Henry's constant. Clear? KH will be your Henry's constant. Okay, so in this way Henry tried to get a relationship between the partial pressure of the gas and the mole fraction of a gas. If when I say he got a relationship between partial pressure of the gas and mole fraction of the gas, I can say Henry got a relationship between pressure of the gas and solubility of the gas, which was our statement written before. Okay, now we have understood what is what Henry wants to say and all that. Now, okay, we need to understand more about the Henry's constant and how are all these terms related to each other. On what factors that Henry's constant depend? Does it depend on temperature or pressure? What? That we will see now. Now let us see factors affecting Henry's constant. Now this is the equation. Okay, so from this I'll try to take Henry's constant to the left hand side. Okay, when I take Henry's constant to the left hand side, what will I get? Pressure of the gas divided by mole fraction of the gas. So Henry's constant is equal to pressure of the gas divided by the mole fraction of the gas. Now here children usually do a major mistake here. Okay, by looking at this, they have a false impression that Henry's constant is directly proportional to pressure of the gas and Henry's constant is inversely proportional to the mole fraction of the gas, because pressure of the gas is a numerator term and mole fraction of gas is a denominator term. But this is absolutely wrong. This is not the way you need to understand Henry's constant, because I will tell you, Henry's constant neither depends on the pressure of the gas nor it depends on the mole fraction of the gas. How is that? I will tell you. Now you see, if I increase the pressure of the gas, I am increasing the pressure on the gas. When I increase the pressure on the pressure of the gas, more gas molecules will go into the liquid. When more gas molecules go into the liquid, mole fraction increases, so solubility also increases. So when pressure of the gas increases, mole fraction also increases. So it is not like that Henry's constant will increase if I increase the pressure of the gas, decrease if I increase the mole fraction of the gas. No, that is nonsense. Okay, pressure of the gas and mole fraction of the gas both go hand by hand. When pressure of the gas increases, obviously mole fraction of the gas increases. So Henry's constant will not depend on either pressure of the gas or mole fraction of the gas. I will write that point here first. Henry's constant doesn't depend on pressure of gas. Okay, pressure of gas and mole fraction of the gas. So Henry's constant doesn't depend on pressure of the gas and mole fraction of the gas. Okay, if it is not depending on pressure of the gas and mole fraction of the gas, then on what factor is Henry's law depending on? Okay, now let us see that. Henry's law depends on what factors? Okay, let us write that. Okay, Henry's constant depends on temperature. Okay, Henry's constant depends on temperature and nature of gas. Now, two things you need to understand very well here for the MCQs or any other 1 marker or any question. Henry's law does not depend on the pressure of the gas and mole fraction of the gas. Henry's law depends on the temperature and nature of the gas. No two gases will have the same Henry's constant. If you take oxygen and carbon dioxide will have different Henry's constants. So because Henry's constant is a characteristic number for that particular gas. Okay, if it is CO2, it will have a particular Henry's constant. If it is NO2, it will have a particular Henry's constant. So Henry's constant will depend on the nature of the gas. This is clear. So every respective gas will have its own Henry's constant. We have a table in NCERT regarding the Henry's constant values. When we are doing numericals of this chapter, then we will be discussing that table also. Now we will confine to the theory part. Okay, now when I talk about the temperature, now let us see. Now let us see how does the Henry's constant depend on the temperature. Okay, will it increase, will it decrease, what happens, and all that we will see. Before that, I want you people to understand one thing. Now, if I cross multiply this equation, pressure of the gas is equal to kH into mole fraction of the gas. Okay, kH into mole fraction of the gas. Now I told you when I took the example of the cool drink bottle, when I I have applied pressure, I made carbon dioxide gas dissolve in the liquid. Okay, and I closed the cap, so I fixed the pressure. Okay, so I fixed the pressure, so I can say at particular time where I closed the cap, my pressure is constant. Okay, because pressure, it's not like that pressure will keep on changing. Any system cool drink if you have taken, I have dissolved carbon dioxide in water. Okay, applying pressure, that pressure I have fixed now and I have closed the cap. Now, okay, so the pressure is constant and the pressure is fixed. Now you try to understand, okay, okay, now pressure we have fixed. When I have fixed the pressure, okay, when I have fixed the pressure, for example, I have increased the Henry's constant. Okay, I have increased the Henry's constant. Now, if you are getting a doubt, how do I increase the Henry's constant? By altering the temperature. If I want to disturb the Henry's constant, I will play with what? The temperature. Okay. Now, understand, pressure of the system is remaining constant because I have fixed the pressure of the system. Now, if I have increased Henry's constant, now I told you pressure should remain constant. I told you pressure should remain constant due to some temperature factor or some factor. Okay, temperature factor, Henry's constant got increased. Henry's constant got increased. Okay, the major factor what can affect Henry's constant here? Temperature. Okay, because I am talking about a particular gas here. I am talking about the cool drink system here. Okay, I am talking about the cool drink system. So I cannot talk about nature of the gas because I have not changed the gas. Okay, now altering the temperature, I have changed or increased the Henry's constant. Now, when I have changed or altered the Henry's constant, the mole, what happens to the mole fraction of the gas? Now, this should remain constant, but I have increased this. So, to maintain this constant, this should be less. Makes sense? Pressure should be constant. Henry's constant I have increased. Now, for pressure to remain constant, the mole fraction of the gas should be less, so that this will remain constant. So that this will remain constant. For pressure to remain constant for a system, so that the solubility is maintained, okay, that pressure should remain constant. But by any chance, if I increase the Henry's constant, then my mole fraction should be decreased, so that pressure is maintained constant, and vice versa. And vice versa. If I increase the mole fraction of the gas, then obviously Henry's constant will be reduced. So from this I can get a relationship between mole fraction of the gas and Henry's constant, and I can say Henry's constant is inversely proportional to mole fraction of the gas. Henry's constant is inversely proportional to mole fraction of the gas. Clear? So from this what can I say? I can say that when KH increases, Henry's constant increases. Okay, when Henry's constant increases, okay, okay, or else I can make it more clear like this to understand it in a better way. Okay, I can write Henry's constant is inversely proportional to solubility. Okay, Henry's constant is inversely proportional to solubility. When Henry's constant increases, solubility decreases. I can get one more relationship of temperature here. What can I get? Temperature. Okay, Henry's constant is directly proportional to temperature. Okay, Henry's constant is directly proportional to temperature. Okay, because I told you it directly depends on temperature. So from this I can get one more relation. Okay, temperature is inversely proportional to solubility. Okay, temperature is inversely proportional to solubility. Clear? So remember these three things so that it will become very easy for you in the exam to do the questions. Once temperature is increased, Henry's constant increases, solubility decreases. Once you decrease the temperature, Henry's constant decreases, solubility increases. And these are the proportionalities of this. So this is the concept you need to understand. Don't get confused. Henry's constant will not depend on pressure and mole fraction, but it will depend on temperature. Once you alter the temperature, Henry's constant will get affected. That is the reason your solubility also will get affected. And regarding the nature of the gas, what did I tell you? As long as the gas is same, the Henry's constant for that gas will remain the same. For other, no two gases will have the same Henry's constant. There will be slight difference, definitely. Now I want you to teach one more concept here. In your grade 11, you have studied one equation which is called as your van der Waals equation. Okay, van der Waals equation. In the van der Waals equation, you have two correction terms A and B. I am not talking about the correction term B here. Okay, when I talk about the correction term A, okay, what should I understand by the correction term A? Okay, now this correction term A will give you it is an indication of the liquefaction of gas. Okay, means what, ma'am? What do you mean by that? I'll tell you what do you mean by that. If this correction term A is more, what does it mean? Gas is easily liquid. Okay, gas is easily liquefied. Okay, if correction term A is more, then the gas is easily liquefied. Okay, now from this what can I say? Okay, KH value will be more. Okay, KH value will be less. Solubility will be more. Okay, solubility will be more. So when the correction term A factor, you have studied this in your states of matter or your gaseous state chapter. If correction factor A is more, gas is easily liquefied, means the solubility is more and the Henry's constant is less. Okay, this is not, okay, if you want to remember, you can remember. Okay, this is from your grade 11. Okay, there you have studied that if correction term A is more, gas is easily liquefied and the solubility is more. Here I have just added the Henry's constant term because if solubility is more, Henry's constant should obviously be less. Okay, so these are the factors affecting the Henry's constant. Okay, I hope you clearly understood. It does not depend on pressure of gas and mole fraction of the gas, and Henry's constant depends on the temperature and nature of the gas. So this is about the factors affecting Henry's constant. Now we are going to see a very important graph for Henry's law. Now let us see the graph for Henry's law. Okay, pressure of gas is equal to Henry's constant into mole fraction of the gas. Now if I compare this equation to y is equal to mx, okay, y is equal to mx, where your y-intercept will be pressure of gas, okay, your Henry's constant will be the slope of the, okay, I am writing it in this way now, so let me keep it like that only. Okay, slope will be the Henry's constant, x-intercept is equal to mole fraction of gas. Okay, x-intercept is equal to mole fraction of gas. Y-intercept is pressure of gas. Okay, slope is equal to Henry's constant, x-intercept is your mole fraction of the gas. Now let us plot the graph. Okay, your y-axis, y-intercept is pressure of the gas. Your x-intercept is mole fraction of the gas. Okay, your x-intercept is mole fraction of the gas. Now if you take here, I have already told you people, Kh is equal to pressure of gas divided by mole fraction of gas. Now if I plot pressure of gas against mole fraction of gas, as you people already know, when pressure of the gas increases, mole fraction also increases because the solubility of the gas is more in the liquid, so mole fraction also increases. So it will be a straight line. Okay, so it will be a straight line. Okay, as pressure of the gas increases, the mole fraction of gas in liquid also increases. Now what is the slope here? The slope is your Henry's constant. Okay, because the y-intercept term, okay, the y-intercept term I take it as sine theta, and the x-intercept term I take it as cos theta. Okay, then slope is equal to y-intercept term divided by x-intercept term, so sine theta by cos theta, so it will be equal to tan theta. Okay, m is equal to tan theta, that will be equal to your Henry's constant. So what does the slope of this graph give you? When I plot a graph, okay, when I plot a graph, pressure of gas versus mole fraction of the gas, okay, whatever slope I get will give me what? Will give me the Henry's constant. Okay, will give me the Henry's constant. M is equal to tan theta, that is equal to your Henry's constant. So this is how you should understand. This graph. We have plotted it mathematically by using the straight line graph, which is the y is equal to, this is the linear. Okay, I got a linear graph. Okay, which clearly indicates that when mole pressure of the gas increases, mole fraction of the gas in liquid also increases. So this is the graph for Henry's law. Very simple graph. Okay, but it's better you know the graph, because in exam if any graph based question comes, you should not face any problem. Now we are coming to the last part of the theory of Henry's law, which is the applications of Henry's law and limitations of Henry's law. So let us quickly see applications of Henry's law and limitations of Henry's law. Now let us see applications and limitations of Henry's law. If you see the applications, the first application I already mentioned in the introduction only, because it's a very important and easily understandable example. To increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. When you seal your seal your bottle with cap under high pressure, the solubility of CO2 in water will be high. Now once you open the cap, you are releasing the pressure, then the solubility decreases. That is the reason to maintain the fizziness in the cool drinks. What law is applied here? Henry's law. Because the more the pressure you apply on the gas, the more the gas will go into the liquid and its mole fraction will be more, solubility of gas in liquid will be more. So what law are they applying here? Henry's law. Okay, the more the pressure applied uh, on the gas, CO2 gas, it goes more into the liquid and the solubility will be more. You will get that fizzy feeling. Or else I told you, you will get the feeling of some sugar water. Okay, next one. This is a very important example. Before going to that, let me explain you this condition. We have scuba divers, right? We have scuba divers who go deep into the ocean. Okay, who go deep into the ocean. Now, when they go deep into the ocean, what exactly happens to their body? Let's try to understand. When they go deep into the ocean, the pressure is very high. Okay, the pressure is very high deep in the ocean. Now, people have studied, now the deep you go into an ocean, the pressure will be more. The pressure will be more. Now, when the scuba divers go deep into the ocean, there is lot of pressure. Okay, there is lot of pressure. Because there is lot of pressure deep inside the ocean, all the gases will easily get soluble in the body. In the body, what is the liquid we have? Blood. So all the gases which are there in the surroundings, in the water, okay, all those gases get easily dissolved. Okay, in the water also you have your dissolved gases. So whatever gases are there surrounding the scuba diver, because of the high pressure which is there inside the ocean, they get very highly soluble in the blood. Okay, now the condition is the scuba diver is deep in the ocean. Because of high pressure, all the gases are very much soluble in his blood. Now what will happen? The scuba diver will not stay lifelong there only. You know? He will he will slowly come up. Okay, he will slowly come up. Now when he is coming up, what will happen? Now when he is coming up, okay, now when he is coming up, the pressure starts decreasing. Because deeper the pressure was more. Now when it's coming up, the pressure will start decreasing. Now when the pressure starts decreasing, the solubility of gases in the blood also decreases. So slowly the gases which were dissolved in the blood, they start coming out. The gases which were dissolved in the blood when you went deep into the ocean, now when you came up, due to the less pressure, slowly the solubility of the gases in the blood decreases, and slowly the gases will start coming out of the blood vessels. Now, you people know that when I talk about gases, you have your nitrogen gas. The majority is your nitrogen gas. Nitrogen basically is a big molecule. Okay, N2 is a big molecule, and maximum of the gas which can get dissolved is your nitrogen. Now, when the gases are coming out, with nitrogen being a bigger molecule and in larger quantity, when the nitrogen gas is coming out of the blood vessels, there will be a rupture kind of thing in the blood vessels, or there is a condition where the blood vessels face a special condition. Here we call them as bends. Okay, what do we call the special condition as bends? Okay, so that is the condition which we call it as bends. What is bends? When a scuba diver goes deep into the ocean, because there is more pressure deep inside the ocean, the solubility of gases is very much high. So all the gases will get soluble in the blood. Now when the scuba diver is coming up, okay, the pressure decreases, so the solubility of gases in the blood decreases. So the gases, especially nitrogen being a heavier molecule and in larger quantity it is present, it comes outside the blood vessels, causing a very painful condition. The blood vessels are under a lot of strain, because all the gases are at once, okay, majority of the gas, that to nitrogen gas, is at once coming out. That painful condition is called as your bends. That painful condition of blood vessels, when gases all of a sudden come out, that condition we call it as bends. That is the reason even the scuba divers, okay, if you observe the scuba divers, they don't come all at once onto the top. They come slowly, because when they come very quickly, due to the sudden change in the pressure, the blood vessels get ruptured. To avoid this problem, the scuba divers don't at a time come up. They slowly and steadily come up. Okay, so now now we can't we can't allow scuba divers to get hurt. Okay, to get hurt. So there should be a solution. Now when we talk about the solution, here if you see the solution, to avoid bends as well as toxic effects of high concentration of nitrogen in the blood, the tanks of scuba divers, if you see the scuba divers carry a tank behind them when they go for diving. Okay, they carry a tank when they are going inside. The tanks of scuba divers are filled with air diluted with helium. Okay, now why do scuba divers carry a cylinder, carry a tank or a tank kind of thing in which you have helium? What is the reason for involving helium here? Now let us see the role of helium here. Okay, the scuba diver went inside. Okay, all the gases got dissolved so much because of high pressure deep inside the ocean. Now when the scuba diver is coming up, now in the tank, helium is there. Okay, now helium is a lighter gas. Now when the dissolved helium is a very lighter gas, so it easily gets dissolved in the blood also when the scuba diver was deep inside the ocean. So it gets easily dissolved in the blood. Okay, fine. Now when the scuba diver is coming onto the top, okay, now the condition is understood because the pressure reduces, the gases come out of the blood vessels. Helium will come out of the blood vessels, but we have avoided the problem of bends because helium being a lighter gas, when helium gas is coming out of the blood vessels, you don't feel that much pain. Previously, it was nitrogen in abundance, and nitrogen was a heavier molecule. Nitrogen, first of all, has toxic effect. Second thing, when nitrogen gas is coming out of the blood vessels, being a heavier molecule, the nitrogen gas, when coming out, causes lot of pain. Now, we have avoided two things. Helium gas being a lighter gas, when you go inside deep into the ocean, it gets easily dissolved. Now, when you come to the top part of the ocean also, helium gas, when it is coming out of your blood vessels, will not cause you that much pain because it is a lighter gas. Clear? And one more advantage is we have avoided so much concentration of nitrogen, so toxic effects of nitrogen also we have reduced. So to avoid bends, what the scuba divers do? To avoid bends, the scuba divers tanks are filled with air. They carry air, but usually what does air contain? Nitrogen in maximum amount, then oxygen, then all your other gases. But now what we are doing, we are taking air and we are diluting it with helium to reduce the bends problem. Clear? This is a very important example and very important application of Henry's law. Many times asked in the examination. Now the next condition is a very common observation you people have seen if you have gone on to mountain trekking, or if you have gone to very high altitude areas. When we go to very high altitude areas, the very important problem we face is anoxia. Okay, and now if we see what is anoxia, okay, when we climb to higher altitudes, climbers become weak at higher altitudes and unable to think properly due to low oxygen levels. Now you people know this concept that due to gravity, most of the molecules are towards the surface of the earth. Most of the gas molecules are towards the surface of the earth. Now when you go to the higher altitudes, the pressure of oxygen in the air is very less, or I can say the quantity of oxygen in the air or the percentage of oxygen in the air at higher altitudes is very less. Clear? The percentage of oxygen at higher altitudes is very less. Now when you go to higher altitudes, because the percentage of oxygen is very less in the atmosphere around you, you can't take so much of oxygen into your body. Right? Now you people know for any metabolic process in your body to happen, you need oxygen for it. Now due to the lack of oxygen there, what will happen? What happens? Due to the first of all, when you go to higher altitudes, there is less pressure. Okay, there is less pressure because you don't have much of atmosphere. Now whatever oxygen which is present also, it will not get soluble in blood. It will not get soluble in the blood. So your body, first of all, low oxygen, whatever oxygen is there also in the atmosphere, that will not get easily soluble in your blood. So your body is in such a condition where it is in complete deficit of dissolved oxygen in blood. Now you know oxygen being dissolved in blood is very important for proper functioning of our body and especially our brain. Now due to this lack of oxygen in the blood, okay, what condition do we face? We are not able to think clearly and our body becomes very weak. If oxygen is not there, how can a person be strong? All the metabolic processes will become very weak. There will not be proper blood supply to the brain, so the person will not be able to think properly. What do you call this condition as? This condition we call it as anoxia. Okay, so these are some applications where we can easily see the application of Henry's law, because anywhere you see here, pressure and solubility are very much connected to each other. That is the reason these are very important applications of your Henry's law, which explains the dependence of pressure of gas on the solubility of gas in liquid. Now, Henry's law definitely has limitations because Henry's law is not applicable in all conditions. Let us see why and how. Point by point we will see. Henry's law is not applicable when the solution is dilute. Okay, now I'll tell you something. Okay, when the solution is dilute, please not try to understand what does Henry's law say. Henry's law talks about the application where you apply pressure and the gas gets soluble. and the gas gets soluble. Now, when I'm talking about a solution which is very dilute, okay, very dilute, which has very less molecules of gas dissolved in it, I cannot talk about the relationship of pressure and mole fraction, right? Because already the quantity of solute which is there, the solute is what here, gas. Already the quantity of solute in the gas is very less. Now I cannot relate the how much ever pressure I apply also, because the solution, okay, the solution is very dilute. You can't get a proper relation between partial pressure of the gas and the mole fraction of the gas, because the solution is in very dilute condition. It is applicable to less soluble gases. Now this is very important application. When we say it is applicable to less soluble gases, I will tell you what does it mean. Now there is a gas, even if I apply little bit pressure also, it will go completely into the liquid. Means what? You need not do so much work here. You need not do so much work here. Little bit pressure you apply also, the gas will go happily and get dissolved in the liquid. Now here there is no point that you are increasing the pressure, then the gas is going into the liquid, and then the mole fraction increases, then the solubility increases. Do you have any relation like this? No, because you need not do any much of the job of increasing pressure and increase the mole fraction, by that increase the solubility. Okay, the gas get easily soluble because the gas, the gas is highly liquefiable. I told you in van der Waals there is a correction term called A. Its A factor is very high. So when the gas is easily liquefiable, it will happily go into the liquid. In those cases, you can't get a relation of pressure and mole fraction. There is nothing like that, because the gas directly goes into the liquid very happily by applying very less pressure only. So in that case, we cannot apply Henry's law. Now, if you see the third limitation of Henry's law, now if you go back to your grade 11, in gaseous state or states of matter chapter, okay, you people have studied something called as ideal gas. Okay, ideal gas. Now, ideal gas is something which doesn't exist normally, or it is a hypothetical condition. It is a hypothetical condition where, see, if you want to achieve ideal gas condition, you have to maintain a very low pressure and high temperature. At very low pressure and high temperature, a gas will behave as an ideal gas. So what is the condition for a gas to be called an ideal gas? You should maintain low pressure and high temperature conditions. Okay, behaves ideally and less soluble in the liquid. So ideal gas basically is less soluble, less soluble in the liquid. Now I told you, if it is less soluble, I told you previously also. Okay, if it is very highly soluble, immediately gas is going into the liquid, I can't apply. But if it is less soluble, in case of less soluble, then your pressure will play a major role. Because it is less soluble, now I need to apply pressure. Now the mole fraction of gas in liquid increases and solubility increases. That is the reason when we talk about ideal gas is a gas which is at low pressure and high temperature. So for ideal gases, okay, see, in ideal gases, for ideal gases, what will happen? You can easily apply Henry's law, because ideal gases are not that soluble in the liquid. Ideal gases are not easily soluble in the liquid. Now, when something is not easily soluble in the liquid, your Henry's law comes into play. Okay, so you can apply Henry's law very happily for ideal gas, because ideal gases are not that soluble in liquid, or they are less soluble in liquid. Okay. Okay, so Henry's law can be applicable in this condition, but Henry's laws cannot be applicable in that condition where the solubility is high. So please remember, Henry's law cannot be applied in the case where the solubility of gas is high. Very important point. Okay, Henry's law can't be applicable when gas chemically reacts with the liquid solvent. Now you have many. Now when you have certain gases which react with liquid solvent. For example, if you take water and ammonia, ammonia being the gas, when you pass ammonia in water, ammonia reacts with water. Okay, ammonia reacts with water, forming ammonium hydroxide. Now, how can you get a relationship between pressure and mole fraction of a gas when the gas is reacting with the liquid solvent? Am I right? Okay, basically Henry's law is getting the relation between the applied pressure and the mole fraction of gas in liquid. Now when the gas is going into the liquid and reacting with the liquid, now I can't get the relation between the applied pressure and the mole fraction, because now there is no ammonia only in the liquid. Then how can I talk about mole fraction of ammonia in the liquid solution? Okay, so in that cases where the gas is getting reacting with the liquid, I can't apply Henry's law. Okay, so limitations I told you, you can't apply it for dilute solutions, you can't apply it for highly soluble gases, okay, and you can't apply it for gases which go and react with the liquid solvent. So these are the applications and limitations of Henry's law. Now let me teach you the effect of temperature. Okay, let's go to the effect of temperature on the solubility of gas in liquid. I taught this partially when I was doing Henry's constant, but I want you to teach this topic in terms of Le Chatelier's principle. So now we'll do effect of temperature. Let us understand the effect of temperature on solubility of gas in liquid with respect to Le Chatelier principle. We already know that previously I taught you using the Henry's constant part that when I increase temperature solubility decreases, but we have been doing in this in terms of Le Chatelier's principle as we did in solid and liquid. So let us try to do it here also. Now when I talk about solubility of gas in liquid, we know that gas, okay, gets soluble in liquid. Okay, gas gets soluble in liquid. Am I right? Gas gets soluble in liquid, and you know now gas is in which form? Okay, gas is in which form? Liquefied form. Okay, gas is in which form? Liquefied form. Now when you compare this process, gas going into liquid and getting dissolved, I can call this as a type of dissolution. Okay, I can call it as a type of dissolution. Am I right? Dissolution. Or passing gas into a liquid and gas getting soluble into a liquid, you can call it as a type of dissolution, or you can also call it as a type of condensation process. Okay, you can also consider it to be type of condensation process. Okay, because we are talking about gas becoming a liquid. Okay, we are talking about gas becoming a liquid. Okay, so I can also call it as a type of condensation. I can also call it as a type of dissolution because gas is getting soluble into a liquid. Okay, now when we talk in terms of dissolution or when we talk in terms of condensation, because we are talking about gas going into liquid and becoming liquefied. Now these two processes, okay, now these two processes, when we talk about the energetics of these two processes in terms of heat, they are exothermic processes. They are exothermic processes. Okay, means they involve the liberation of heat. They involve the liberation of heat. Now when I was teaching you Le Chatelier's principle, when I was doing solubility of solid and liquid, I clearly told you for an exothermic process, if it is an exothermic process, then according to Le Chatelier's principle, okay, according to Le Chatelier's principle, for an exothermic process, what should happen? For an exothermic process, solubility decreases with increase in temperature. I clearly told you in the previous class also, if it is an exothermic process, according to the Le Chatelier's principle, solubility decreases with increase. Okay, solubility decreases with increase in temperature, and vice versa. Okay, if I increase the temperature, solubility decreases. If I decreases temperature, solubility increases. That is the reason when you bring cool drinks or soda drinks, you put it in the refrigerator, because when the temperature is low, the solubility of gas and liquid is more. Now when you bring a cool drink or soda drink outside, means what? You are increasing the temperature. Now when you increase the temperature, what happens to the solubility? Decreases. So the gas starts coming out of the liquid. This is the logic why they are always stored in a cold condition, so that the gas will be more soluble in liquid. Okay, now what can I write here? Okay, now what can I write here? When we talk about solubility of gas in liquid, okay, solubility of gas in liquid, is inversely proportional to temperature. Okay, solubility of gas in liquid is inversely proportional to temperature according to the Le Chatelier's principle concept. because it is a process of dissolution, it's a type of dissolution, or it is a process of condensation, type of condensation, which both, okay, which are exothermic processes. And according to Le-Chatelier's principle, for any exothermic process, temperature is inversely proportional to the solubility. That is the reason, as solubility of gas in liquid is an exothermic process, it is inversely proportional to the temperature. Okay, with this we complete the full theory part of Henry's law. What have we seen from the starting of the session? We have seen what is the relationship between pressure and mole fraction. Henry's law gave a relation between pressure and the mole fraction of the gas, which is in turn called as solubility. Then we have got a constant called Henry's constant. We have seen on what factors does Henry's constant depend and on what factors Henry's constant doesn't depend. Then we have also done the graph for the Henry's law. Okay, then we have seen applications and limitations of Henry's law. Now at last we have seen effect of temperature on the solubility of gas in liquid. With this I conclude today's session. In the next session we'll be seeing numericals on Henry's law and different questions on Henry's law, which are very important. Till then, okay, keep watching my channel, keep loving my channel. Bye bye.